So in the previous lecture, we talked about behavior acting as temperatures and using Newton's law of cooling to predict certain behavior of a person at a specific time, or a decision at a specific time, given some initial influence outside. So like outside temperature, inside temperature, rather outside temperature affecting inside temperature. So in today's lecture, I'm going to be talking about conversion armaments. So this is the first of two branched lectures or related lectures called conversion armaments. Conversion armaments. And it's basically what its name states. How do we convert a given population into a bunch of femboys, or traps, or some whatever we want, done by gas or various other things. But we're not really going to focus on the physical part of it, but more on the mathematical part of things. So through some chemical experimentation, maybe provide some background. Through some chemical experimentation, it's been found that the rate of change, or rather, that if a certain substance is being converted into another substance, the rate of change of the amount of the first substance changing to the second substance is proportional to the substance itself, right? So, or the unconverted substance. So, if we let A be a function of t, our differential equations a dot is equal to negative k. A dot is equal to dA over dt. Now this is not appearance. I'm not saying appearance, and this is not wearability. This is not W. It's just an example. So if we're converting one substance A into another substance B, and this is the quantity of A, if this A, a function of t, is a quantity of A, it satisfies this differential equation. Or we need a function A that satisfies this differential equation. It's a simple chemical conversion. There's no other factors such as entropy and amount of substance that affects it. We're assuming that these two are equal substances and stuff. Sorry for the noise in the background. So these two are substances with equal amount, and the amount of A, or unconverted substance, is rate of change of the conversion is directly proportional to the substance amount, or the unconverted substance. So now you can probably deduce how we apply this into the study. I'm just going to say the answer right now, because the solution to this differential equation is not the focus of the study, but rather our application and the intuition behind it. So I'm just going to say downright that A of t is equal to C times e to the negative kt. K is a proportionality constant over here, t is our variable, and C is the initial amount of the substance. So we're given a boundary value problem, or initial condition, two initial condition, or a bunch of initial conditions, and we're asked to solve this equation. We just put the initial conditions over here and find necessary stuff, right? So at a certain time t, the substance A is this amount. We're just gonna input it here and find C. Actually, it's already stated here in the book that C is essentially x sub 0, or our initial condition. So we're trying to find the proportionality constant k given those initial conditions in this solution. I'm just gonna say it right here, because finding the solution or computing the solution is not my focus for this entire course, but rather how we apply it, and how it applies to our study, and how do we use it, and how do we develop intuition for it. So how this simple chemical conversion process and differential equation, and how does it relate to our study? So suppose we have an initial population 0 at a certain time 0. So we have these guys, and we want to convert them, or we want to start converting this population into a bunch of femboys or traps or whatever we want to convert them to. This will involve chemical conversion, assuming that the population doesn't really notice that the chemical is like affecting them. So either we affect the water supply so that they're drinking water that makes them want to be more gay or whatever, or we spread aerosols into the air that converts them, like a conversion gas. That's actually the first one here. The trap conversion gas. This lecture. Next lecture is going to be a different one. It's more of a logistic kind. That's for the next one. So we're given an initial population of p sub 0. P is a function of time. P is a function of time. I'm gonna denote it by a row, the small letter one. Now, given these initial conditions, we essentially set up the problem as rho dot is equal to negative k rho, or dp over d p of t is equal to negative k p of t. This is our differential equation. So now we already know that p of t, or I'm just going to write it rho. We already know that rho is equal to c e to the negative kt. So our population is at any time t can be determined via these things, where in c is simply our population 0 at this time here. Alright? And we just find the proportionality constant given these things. So, okay, let's do an example. So, I'm just going to write here, rho dot is equal to negative k rho. So now, let's say that at the time 0, time 1, wherein it's let's say 3 seconds into the start, or after releasing the chemical or the gas or the liquid or whatever, what have you, the population that's converted already, or the amount of unconverted substance or unconverted population, p sub 1 is, p at c sub 1, t sub 1 is say 46 people. 46 people. Unconverted. Now, at this time, so now we wish to know what's the amount of people that's unconverted after, let's say, 6 seconds. Goal, find uncon people at t sub 2 equals, let's say, 10 seconds. 10 seconds. Problem. Theorized problem. We already know that rho is equal to c e to the negative kt, and our c is essentially rho, which is 46. And so, yeah, we just input it here. 46 equals 46 e to the negative kt. But at 46, our t is 3, so that's 3 over there. So now we just find our Mr. Constant, cancel that out. 46 divided by 46. And we get e equals 1. Actually, 1 equals e to the negative k. Take the ln of both sides. ln 1, I'm just going to write ln because it can be thought of like that. And then the ln of e negative k3. And so ln of 1 is 0, and that's negative k3. Divide by 3, and our proportionality constant k is 0. And that checks out because 46 equals 46 e to the negative 0 times 3 would give us 46 equals 46 times 1, because e to the 0 is just 1, or any number raised to 0 is just 1. And that's 46 equals 46, check. It's a good check, not a sanity check. Now, we want to know, we already know our proportionality constant K, given these initial conditions. Now, we wish to know the unconverted people at 10 seconds. So, I'm going to write our solution here, our general solution. Rho equals, what's it called? Rho equals C e to the negative kt. Alright, so now we wish to find the unconverted people at t sub t equals 10 seconds. And our initial population is 46 people. So let's just let's find rho after 10 seconds, proportional to constant. So that's 46. Oh no, wrong, sorry. Rho sub 2. This is essentially our rho sub 2. We're evaluating it at 3 seconds. Given our initial population and our proportionality constant. Proportionality constant is 0. Okay? I'm just gonna note that down. Proportionality constant is 0, and our initial population is 46, and we wish to find the amount of unconverted people at 10 seconds. And in a second, you will see that no one gets converted. Alright? You'll see that no one gets converted since our proportionality constant is 0. So therefore, no change will happen to the population. So, yeah, so let's just complete the problem. So we have our initial population 46 e to the 0 times 10. And that is still 46. Because e to the 0 times 10 is 0. E to the 0 is 1. So that's 46. So our conclusion is that at 10 seconds, no one is converted. And from here we can say that the population is immune to the gas or the water or the chemical or what have you, because our proportionality constant is 0. Alright? Now in most cases, or maybe in all cases, our proportionality constant is given, and we can just plug the necessary values into our general solution to find or to conclude stuff about the problem or to solve the problem. But I think I wanted to show how to find K in certain instances here. Alright. So that's that. Let's go for another. I wanted to go for another example. This time K is given. I'm gonna pick a problem from the book. So if you want to follow along, you can go along with me. Alright. I may need to cut this a little because yeah. So let's pick on the next page 66, chapter 4, elementary applications. Suppose that a chemical reaction proceeds according to the law given in the previous section, or the discussion that I just said. If half the substance A has been converted at the end of 10 seconds, find when 9/10 of the substance will have been converted. So if half of the population, P is converted, so P is converted, half of the population P is converted at the end of 10 seconds. So P becomes B, half of it, 1/2 P becomes B in 10 seconds. So population starts to become femboys in 10 seconds. Alright? Find when 9/10 of the substance has been converted. So 9/10 of P. We're trying to find when 9/10 of this substance becomes this. So half the population first, and then we gotta find out when approximately 90% of it, 90% or at least 9/10 of this population is. So seconds. So that's our find. So so let's assume that the population is 100 individuals. So in the span of 10 seconds, 50 individuals, there's the time limit on YouTube. So I'm just gonna discuss this I'm gonna continue this in the next section. It's optional, right? So yeah.